Hey everyone, let's try to solve another LeetCode problem today. Today's problem is called maximum elegance of a k-length subsequence. In this problem, you are given an array of pairs, pair of numbers with two values. So in this case, the last value will be something called a profit, while the second value will be something like a category. And you are also given an integer k. K means that how many numbers you can pick. So with the items in k, what you want to do is to pick k number of items in the given items array. It can be the first two, or it can be the first and the third, or it can be the third and the second. It doesn't matter. They don't have to be continuous. You just have to pick k of them. And after picking k of them, you will get a score for your selection. Basically, the score will be the sum of profit for each element that you have picked, plus the distinct number of elements considering the category. And you can pick that element and do a square on it. So in this case, the answer is 17, is because you can pick the third one and the first one like this, and the sum of the profit is 3 plus 10 will be 13, and the distinct number in there considering the category is 2, because 1, 2 are different numbers, so the distinct category inside your selection is 2. So we apply square on that, will be 4. And eventually we will get 13 plus 4 equals to 17. And this is how the 17 is calculated. Let's take a look at the second example. This time you are given an items array of 4 elements, and you are also given k equals 3. And the answer is 19. Why? It's because you can pick 3, 1, 2, 2, and 5, 3. So the sum of the profit is 3 plus 2 plus 5, which is 10. And the distinct category of your selection is 1, 2, 3. All of them are unique, so you have 3 distinct elements. That's why 3 squared is 9. And we sum them up, we get 19, which is our expected answer. So we don't have to explicitly tell how to make this 19. We just have to return this is the maximum that we can get. So how can we solve this problem? As I already mentioned, if you look at the answer, the formula will look something like profit sum plus distinct square. So it seems complicated. Why don't we just try to ignore the second part altogether first? If we ignore the second part, it means we don't care about the category at all. If we don't care about the category, we can just sort all the items by the first value, which is the profit. And then we will get something like this, which is already sorted by the first value, which is the profit. This is natural to just start from the largest because we want to maximize the profit. So we start from 10 and then we go 5 because we can pick 2 elements. So we just pick the 2 most profitable items. So after doing that, we will have pick 5, 1 and 10, 1, something like this. At this point, what do we know? We know for sure that if we don't care about the category, this will be the best that we can get. And we also know that this selection, although we don't care about the category, it must fulfill the distinct equals 1 requirement. Why? Because in a worst case scenario like this, you selected the k most profitable items, and all of the k most profitable items happen to be of the same category. So basically it's this case. But even if it is in this case, we will have a distinct count of 1. So we basically fulfill distinct equal 1. And this is the maximum we can get if the distinct equal 1. At this point, you might ask, what if the most selected k profitable items are not all the same? For example, this could be 2, or this could be another item, it could be 3, but we don't care about them first. We're going to iterate every distinct possibility one by one. So if it is okay, then we keep increasing the distinct count. If it is not okay, then we will do something else in order to make it okay. By okay means having distinct in selection greater or equals to the current square that we are trying to apply. So if we are trying to apply distinct equals 2, then this selection, the original selection here is 10, 1, will not be okay because we cannot apply distinct equals 2 in it. Basically, we cannot sum 5 and 10 and plus 2 square on it because it doesn't work. That's why we have to give up something. It means that we have to delete some old element in our selection and add some new element and make the distinct count increased. But the question is what to give up in the selection that we have picked. So let's take a look at this diagram. We iterate all the items from the largest to the smallest. Again, the profit is the first value of the pair. And we have picked k items already. Now, we have picked k items, but it doesn't mean that the distinct count is k. It could be something like x, because we have picked k element on it, and there could only be, at worst, there could only be one element that are unique. It means everything else in the set is a duplicate in terms of the category. So how do we increase this x? Well, in this k selected element, if we want to increase the x, which is the distinct number, we can add something in here. So what should we add first? Again, we want to maximize the profits. Of course, we want to add the largest first. So we're going to add this one, and we try to see if it is already in here. So if it is already in here, then we don't bother adding it. Because remember, we are going from largest to smallest. The fact that we have already picked it before, it means that the current element must be smaller than the thing that we have already picked. And what value can it provide? If it is already picked and also smaller than its previous value in the same category, it doesn't make sense to add it. That's why we will just ignore it if we find something that is having the same category that we have picked. Then let's take a look at the second item. Let's say this second item doesn't appear in here. It's a new item. So we can potentially increase x by 1 because this new item doesn't appear in our selection before. But what to give up for this particular set in order to make room for the new item? Well, the answer is again very obvious. We want to give up the least profitable item. But one catch is that we don't want to give up the number of category because we know that on the left-hand side, the profit value will always be greater than the right-hand side. So if we trade any item on the left-hand side in order to increase the category, it makes sense. But if that number is the only number in that category, then it doesn't make sense to give up that particular value. That's why we will give up the least profitable value if there is more profitable item of the same category. To do that, we will use a stack to store duplicate category profit. Well, if we see a duplicate category profit, then we immediately add that to the stack because, again, we are going from the largest to the smallest. If we have seen a duplicate category, it means that there is something larger for the same category. That's why this particular duplicate category profit can just be added to the stack. And when there is a need to increase the distinct number of category, then we can pop the least profitable item in order to make room for the new element. So that's pretty much all the idea of the solution. Let's take a look how can we implement it. So first we're going to initialize n as the size of the items. Then we're going to sort items by the birth value of the pairs, which is what the built-in Python method will do by default. But we want to set reverse equal true because, again, we want to visit the items from the largest profitable item to the least profitable item. Then we're going to set a scene category to indicate what category that we have seen. And this stack will store all the profit that can be discarded. Basically, that is all the profit that has a larger profit for the same category that has appeared before. That's something that we can discard in order to make a new category to be inserted. So we're going to start the answer from 0. And in this loop is what I explained before. This is when I just try to insert everything without considering the number of category at all. We're just going to add it blindly. And then we also need to check if this category has already seen before on the left-hand side. Because again, we are visiting from largest to smallest. And if we have already seen the category, it means there is something larger than me for the same category. That's why this is something that can be discarded. That's why I added to the stack. Otherwise, I will just mark this as a new category. And then we have considered everything from 0 to k minus 1, which is the top k items in terms of the profit. Then the next item we can consider is k. Then we're going to initialize the current, means the current sum of profit as answer. Then we're going to iterate all the square number possible. In the worst case is everything being the same in the category for our selected items. In the best case is we select k items and all k of them are being distinct. So then, if the length of the scene category, namely the distinct number for our selection, is less than SQ, it means that if we want to apply SQ square on our selected value, we have to do something. Basically, we have to increase the distinct number. Then we're going to go through every number that we have yet to add and try to see if we can add that to our selected values in order to increase this distinct number count. So if it is already inside the scene category, then we're just going to ignore. This while loop basically will loop until we have find something that is new in terms of the category. But there is a case that when there's nothing to add, we basically just cannot find a new category, then we will just break because we cannot do anything more. Otherwise, we have find something to add in order to increase the category count. So we want to give up, as we mentioned, the least profitable item, which happens to be at a stack top, because we are visiting everything from the largest to the smallest, and we will add the profit from largest to smallest as well. So the stack top will be the smallest in terms of the profit. That's why we can give up the value here and then add this new item. And after adding this new item, we will mark the scene category for this particular item as well. Now, after we have done it, and we are not breaking in here, it means that we can apply square plus 1. Basically, we can apply at this SQ square to our current selection. Then we will try to see if it is larger than the answer. And if it is, then we'll update our answer to it. And eventually, we will just return the answer. This is what we want. So in terms of the time complexity, we need O(n) log n, basically come from the sort here. And for the space complexity, we need O(n), basically coming from the stack array here, and also the scene category. So that's pretty much all of the solution and the analysis. And I hope you'll find this helpful, and I will see you next time. Bye-bye.